Hello, you
Yes, sir.
guys
Good
able to?
Yeah, good morning, sir.
Yeah, good morning, good evening to you all. You guys able to hear me?
Yes, sir.
Okay. Yeah. So I guess we'll wait for the other guys. I sent you an email.
Yeah, I got the multiple choice questions. I have forwarded to the group.
So we have to decide how you want to do this, and can probably give a little bit of time for people to work on. Or
Yeah, they will do it, sir, after the lecture.
okay. So did you? Are you going to this conference in Bangalore in September?
Probably, I think few of us will go, but it has not been planned yet. What about you, sir? Are you coming?
I I may come. I'm not sure yet totally, but
Okay, okay,
so I'm just wondering, like, if there is still time, you can probably submit a paper on this FWI work.
okay, okay. Yeah,
I don't know if there is time, but they'll probably still take your paper.
okay, okay. I will check, sir.
So you think others would be coming, or you're not sure?
We can start, sir. Most of us, I mean, the one who has to work on FWI, they are here. Rest of them are
Okay.
interns. They'll be joining slowly.
Okay. Okay. So do you see my screen, or rather, do you see my PowerPoint?
Yeah, yes, sir. You can see.
Okay. So based on your request, I think I've added this lecture on redataming, Marchenko stuff. And
Yeah,
then after that, we'll talk a little bit about some basics of inversion. We'll not be able to go into details of inversion in this part, in this, during this course, but we can do it another time. But I'll introduce to some of the issues on inversion before
yes, sir. Yeah.
before we wrap up. So the topic here is redataming of seismic data. And so it's a process where we mathematically transform seismic data from one acquisition datum to another. So without physically reacquiring the survey. So what it means is that if we have, uh, well, we always collect data on the surface and a few boreholes. But if you wanted to have an experiment where the sources and receivers are at a depth, it's not possible to do that physically. So typically we do that, and the way we do that is to apply some kind of mathematical operator on the surface collected data to simulate an experiment that is not feasible to do in a physical setting. And the reason we want to do this is for maybe sometimes creating a common reference surface. If you have multiple seismic data sets, you wanted to have a common reference surface. And one major motivation for doing this was application in imaging and now in interpretation. Okay. So essentially, what we do is we record the wave field and extrapolate it to a new location. And there we use wave propagation principles and all the different methods of wave propagation simulation have been discussed in the last few days. Most of them, may not be all. I didn't talk about finite elements, but most of the methods for wave propagation have been discussed, in which case we just said that we have a source at some location and we wanted to see after initiating the energy at the source how it propagates inside the medium, and what would that look like when you're recording it at some receiver locations. And one thing I just wanted to tell you, that when you're doing this numerically, we can have sources and receiver pretty much anywhere we want, but in practice we cannot do that. So synthetic experiments can give us some idea about what the data might look like if the sources and receivers were at different locations than where you were recording. So what is redataming? Redataming term has been used to just take the data from one particular datum to another datum. So what it means is that let's say that this is our experiment where these red stars are the sources, and say that or maybe red stars are the receivers and these triangles are the sources. And let's say that you have some overburden, it could be anything, so weathered layer or whatever. And what if we were able to collect data at this depth, at this datum? Wouldn't that be nice? Because in that case, we can avoid all the effects of the overburden, right? So in Saudi Arabia, they actually have been drilling holes below the weather layer, and then they're collecting data there. But can we do this numerically? So that part, what Saudi Arabia is doing, is very, very expensive. So can we do this numerically? So let's say that you have these surface shot gathers. So can we just simulate an experiment where the sources and receivers are both at, at a different depth? Now, the reason we need this is that we sometimes have rugged topography in many land experiments. If you go to, say, hilly terrains, the topography is rough. So the source elevation is different. You also have different receiver elevations, and normally this is not much of a problem in the marine data, but land data is a common problem. But this could also happen when you have marine surveys with changing water depth. And then we also have irregular acquisition geometry. Okay, for many of the processing algorithms, uh, we we desire to have regular acquisition geometry. For example, when you were doing a Fourier transform based using a Fourier transform based techniques such as FK filtering or FK migration, and you are using FFTs. I mean, you can do a Fourier transform when there is irregular spacing, but it becomes much faster when you have regular spacing using fast Fourier transforms. So the benefit of redataming would include consistent geometry and improved velocity analysis, because then they're all sources and receivers are lined up, and then you can ignore the effect of the topography there. You definitely have better migration results. And like I said before, you can reduce near surface effects. In some areas, near surface effects are very they're severe. And then in forward modeling, also it becomes easy for a lot of these forward modeling codes. They assume that the free surface is flat. For example, in finite difference, it's kind of difficult to put a rugged topography. In finite element, it can be done easily. It's not that it cannot be done with finite differences, but it's more work. And we can do some target-oriented imaging and inversion. So before I get into the so-called Barchenko, there are two things that I need to explain to you. And the first one is migration. So what is migration? So migration, this is a process, and this is taught like at the very beginning of the migration course, that it's a process of mapping reflected energy back to its true subsurface location. And it's a process which corrects the distortions of the geological structure. For example, if you're looking at the stack data, you have a synclinal structure, but then because of replication, it does not give you true picture of the structure. So by migration, we're trying to bring it back to the true subsurface structure location, true subsurface structure. Now, one method that's been most commonly used is it's known as wave equation migration. In fact, almost all migration methods are wave equation based. So what they do is it actually tracks waves through a medium of known velocity to find unknown reflectors. So in migration, the most important requirement is that you have a velocity model. Okay, only if you have the velocity model, you can basically run the migration. Now, so how does migration work? That is important, and why we need the velocity. So migration, this is an imaging procedure that takes seismic wave fields recorded at the surface as an input, and it calculates the location and strength of reflectors. Okay. So no matter what migration method you use, there are two steps. One is called extrapolation and another is called imaging. Now, first of all, you've heard of different migration methods like Kirchhoff method, and then you also heard about FK migration. You also have heard about RTM and some variants of wave equation based migration. So the way where they differ is the way extrapolation is done. Okay. So Kirchhoff method uses asymmetric ray theory, so it uses an approximate method for extrapolation of the wave field. FK typically assumes a layered medium, and RTM uses finite difference for extrapolation. But the imaging part is the same. But Kirchhoff actually has both extrapolation and imaging. They are integrated into one operator, and that's why it's not so obvious that it's actually doing a two-step operation. Now, this is one example. This is not for migration. This is just for modeling. But I use this particular figure because it actually describes the principle of migration in a very, very succinct manner. So this is an experiment was conducted by Fred Hilterman back in 1970. And he did a lab experiment. It was a post-hoc experiment in the lab in a water tank. This was a particular model that he put in. This is the model of the syncline. And here, the sources and receivers transducers are coincident. And what he did here is, since this is a lab experiment, he had the luxury of putting the sources and receivers at whatever depth he wanted, right? So if you go from here up here, so this is the deepest, this is on the surface, okay? This is on the surface. And you see the typical bow tie pattern here, okay? Look at the structure that is syncline, but this one looks like an anticline, right? So what he showed here is that if you take the source and receivers deeper and deeper inside the model, this triplication tends to collapse, and then when they are sitting right on the structure, you get a data set which actually looks like the model, right? And our goal in seismic exploration is to be able to get images like this without all of these artifacts. So what he demonstrated is that you have to, he didn't say these things, he was just showing how the data looks like when you have the sources and receivers deeper and deeper. So what this is telling you that as you go deeper inside the model or inside the earth, you are actually getting when you get closer to the structure, a lot of these artifacts, these are not artifacts, these are actually wave propagation effects, but when it comes to images, those are artifacts. They tend to collapse, and then you get the true image. So in this process, what he has done is he has done extrapolation of the wave field, but not numerically, physically. And right at the uh, structural location, he's actually got the imaging conditions. So it's like all of these points start to fire at the same time. So this is a very nice example that demonstrates this. So why am I showing this to you? Because we'll be talking about redataming, right? So redataming basically means sources and receiver going at different locations. And this is an example of doing this physically. So extrapolation and imaging are the two steps. In extrapolation, we from the surface data we reconstruct the wave field corresponding to a different depth. So let's say that I have the sources and receiver at this location, and then I want to extrapolate or downward continue the sources and receiver at some other depth delta z. Okay. Since we cannot do what Fred Hilterman did, we'll have to make use of some theory. We have to make use of math and computing. So here we will use wave propagation model, and this needs velocity. So there are some formula principle. The imaging is basically some formula that allows us to obtain reflection strength. So like I said before, there are two steps in migration: extrapolation and imaging. Today's lecture we're going to focus on extrapolation, but imaging is basically based on some kind of imaging principles. So there are 3 or 4 different imaging conditions that you impose, and integral methods generally perform on a extrapolation and imaging in a single operation, which I already mentioned before. And there's different migration methods that differ in ways than wave field extrapolation is done. Like I said before, you have Kirchhoff methods, you have FK, you have RTM. They are different. They have different names because they use different approaches to extrapolate the wave field. So as you go from Kirchhoff to RTM, this is more and more accurate method for extrapolation. And of course, depending on the method, we make certain assumption of the nature of the medium, like I talked about in the modeling case. So understanding modeling is fundamental to understanding seismology. If you understand wave propagation theory and modeling, you can understand migration, you can understand inversion or anything new that you want to do with it. Okay. So here, this is the fundamental principle. The seismic wave field is propagated using the wave equation. Now, mostly I'm talking about downward extrapolation because from the migration perspective, but it could be anything. Anything you can do upward, you can do downward, and anything. So let's say that I have recorded data at P, X, Y, Z1. Z1 is the recording surface, and then I want to extrapolate it to some P, X, Y, Z2. So Z1 is my original datum, and Z2 is the target data. I already explained to you why we need to do this for migration. But this also is useful in inversion. Why is this useful in inversion? I can give you one simple example. Let's say that I have 3 kilometers of water. Nowadays we are doing deep water surveys, right? 3 to 5 kilometers, and then we have sources and receivers. And I want to do an FWI, and this below I have another 5 kilometers, right? Now, when you run a finite difference-based simulation, it needs to propagate the wave field all the way from the surface through the inside of the medium. But to be able to do that, it has to propagate the wave field through this water layer, which is 3 kilometers. And that is a waste of time, computing time. So if we had the sources and receivers all at this particular depth, we can completely avoid doing that. Okay, so redetermining the data and doing an FWI saves us a lot of computing time. Now, it's easy to do that when you have the water layer because we know the velocity of the water layer. But if you want to bring it, say, down to this depth through some sedimentary layers, we have to know the velocities to be able to do that to use the existing methods. So, common redetermining methods. One is, static corrections. Sometimes we just simply apply static corrections. It's not a full wave theoretic approach. It assumes vertical ray paths, and it works only when you have mild changes in the velocity in the elevation. We have Kirchhoff redataming. It uses integral solutions. It handles complex geometries. So this was the first redetermining method that was proposed. And there are many folks who are using this Kirchhoff redetermining for you know, FWI. Prior to doing FWI, they just redetermine the data using Kirchhoff redetermining. There is also Gaussian beam redetermining, which is not a lot different from Kirchhoff, except that the Green's functions are the Gaussian beam Green's function. Now, wave equation basically solves wave propagation directly. So what we showed you earlier is how to propagate the wave field forward in time. So starting from t equal to 0, we were going forward in time. So can we just also propagate backward and things like that? So these are things that you can do using wave equation. And the good news is that it actually can handle accurate and complex structures, which is not possible to handle using Kirchhoff. Because in Kirchhoff, you have multipathing, and that is generally not handled very well. So these are all completely model driven. Okay, model driven in the sense that you need to have the velocity model. Then there is another class of methods. It's completely data driven, and these methods, they do not require velocity. And in this category, we have interferometric redetermining and Marchenko series. Okay. So this Marchenko series actually was developed after interferometric redetermining was proposed. And it was essentially, first it was rehashing of interferometric principles, but later on they put it in a series and made it even more attractive. So I'll talk about how they work. So first of all, let's look at the model dependent and Kirchhoff-Helmholtz integral. So in the Kirchhoff case, let's say that I'll just take the acoustic case. I showed this to you earlier also. So that I have a point x1 and this is a volume. And this point x1 is outside the volume and there is a point x2 which is inside the volume. So this is my Helmholtz equation or in frequency domain. It's a wave equation in frequency domain. So I have f1 which is here, force, and I have f2 here. And the thing is that f1 actually vanishes inside v and delta v. Okay, so because this is outside. So here we'll use this famous Green's theorem where we just do this n dot. We just transform this volume integral into surface integral and do a little bit of algebra. And then if I put f2 as a delta function here, what I get is this equation. Now this is fundamental to doing Kirchhoff propagation or imaging. So what does that tell you? There are two wave fields here, P1 and P2. So P1 is from F1 and P2 is from F2. These are the two sources. So what this tells you is that you can compute the wave field at x2 from a source at x1 by integrating along this surface. And for that integration, you need P1 and P2 along this surface and their gradients. Okay. And of course, if you were talking about Green's function for point forces, then this basically takes the form of Green's function. And here in this Green's function, we can use ray theory or you can use beams or whatever. And this was the principle of Kirchhoff modeling. So the way it works is that we say that I have my sources here and the receivers at here. So and this is my reflector. So I will basically compute the wave field from the source here Then I take each receiver and compute the wave field from the receiver along this. And then I will use this integral. And essentially, I'm just summing the contribution from here. Okay. So given the source and receiver, I have to be able to compute Green's function along this reflector, and then I can use this integral to compute the wave field. So how do we use that for redetermining? This again, you can use Kirchhoff integral for seismic data redetermining. Mathematically, that extrapolates surface recorded seismic wave fields to a simulated virtual data, a complex topography and weathering layers. So originally, this was introduced for post-stack data, and then it was extended to pre-stack for handling rugged terrain and other non-physical static shapes. So this is what happens here. You want to go from acquisition surface to here, right? So you can think of this as so you can compute this travel times, and then you can use that sum over all of this particular surface. So this becomes my integration surface. And then I can, these are my unknown source receiver locations, and then I can integrate this. So all we do is turn it around. We assume that we have fields at the receiver, we have the sources and receivers on the surface, and we're computing the response from a particular depth. But we have the response at a particular depth. So what we do is we assume that there's a virtual source somewhere, and the contributions are coming from, and those are the ones contributing to here. So what I mean is that you can think of this is that it's basically Huygens principle, right? Here we're saying that these are the sources that are propagating the wave fields to the interface. So then you can think of these as diffractors, and then these are secondary sources that are coming in there, right? So I can try to take these wave fields that were recorded here and use that as my integration surface to now redatum this. And this was first proposed probably in the late 70s by Weston Gico, and they used it for regions with topography, and the only thing that required is computing the travel times because it's a Kirchhoff based method, and of course you have to know the velocity to be able to do that. So this worked out better than your static correction. So the limitations here that this is essentially a linear operator, so it relies on single scattering, okay, and so Born approximation. So the multiples from within the over button are not removed, and if there are multiples, they appear as artifacts. And of course, Green's function must be known, and to be able to compute the Green's function, we have to know the velocity structure, right? And then other thing is that this method that I showed you earlier, that ray theoretic Kirchhoff method, also does not include transmission losses. So besides the fact that it needs a velocity model, the approach does not include multiples, it does not include transmission losses. And Marchenko actually overcomes all three limitations. It does not require a velocity model, it includes multiples, and includes transmission losses. So before we talk about Marchenko, let's look at interferometry. This was really one of the finest papers that came out in geophysics by John Clairvaux group. What he said is that by cross-correlating noise traces, so you throw in some instruments and just record noise for several days and hours, and by cross-correlating the noise traces, you can actually simulate surface seismic experiment, for example. And of course, he wrote a very small paper for 1D, and this was extended by by several people from Delft University. So here is the idea, is that this is a principle of acoustic daylight imaging. This is also called acoustic daylight imaging. So let's say that I have all of these uncorrelated noise sources, and I'm recording at different locations on the surface. And then I do some mathematical operation, which is actually a cross correlation operation. I'll tell you in a second, between this, and that gives me as if we have a reflection experiment. Okay. And it all depends on where the sources are. So seismic interferometry is actually based on cross correlation representation theorem. So what it tells you is that given a particular source, here we have a lot of sources, right? If you take the Green's function at some receiver x sub a from a source x sub s and cross correlate. So in frequency domain, multiplication of G with G star is this is a complex conjugate, is equivalent of cross correlation. So if you did that, so this one, so you have to remember this. Here is a source, and here is a, these are the recording. Okay, so this is my XS, this is my X sub A, and this is my X sub B. And you have a Green's function recorded here, Green's function recorded there. If you cross correlate and sum over all of these sources, that will give you your, as if you have recorded the data from a source x sub A going to x sub B, and also it gives you its complex conjugate or the negative time. Okay, so it gives you a positive time and a negative time, and this one you can ignore.
Sir,
Yes,
is this the same principle for processing passive seismic?
yes.
Okay.
Yeah. Yeah. So here, so what you see here is that you can generate this. Okay, so typically when you're recording noise, you're getting mostly noise that are horizontally traveling. So you're not able to get the body waves. But if you design your experiment properly, you can get body waves. Otherwise, surface waves are very, very well recorded and very well developed from this cross correlation function. Okay. So here is a synthetic experiment that was done by the Delft group. Here they have these noise sources, and these are the receivers here, and from this particular structure. And this one shows you a transmission gather along the receivers at the free surface. And here is just one trace. And then when they did correlation, as I told you, you have the negative time and also positive time. And then once they did it for all the receiver locations, what you see here is beginning to look like a short gather. Okay. So this shows you reflection common source gather for a retrieved surface source position. So this is as if there is a source at XB at 4,000 meters, and these are all the receivers, and that's your reflection direct simulations with finite difference. So there are still some errors, but some noise, but overall it actually captures most of these, and this is pretty much free of cost because you're just listening to the noise. Okay. Now it has actually matured quite a bit that we are able to see a lot of body waves from this. So this is another shot location. This is the virtual left side is the virtual shot, and this is the real shot location. This is another shot. So cross correlation is basically convolution of one function with time diverse form of the second function. So we know convolution of two functions, f1 and f2, right? So here, if you just do time reversal of one of these, that gives you cross correlation. Okay. So cross correlation is not the same as convolution. In fact, at one time I was giving this talk and one person said, no, cross correlation is same as convolution. So I said, no, it is a convolution, but with the time reversal. Okay, so negative time. And so here is how does it work? It's actually beautiful. So let's say that I have two receivers here, receiver 1 and receiver 2. And I have two plane waves. One is here, another one is here.
Excuse me. So I
Yes.
have a question here.
Yeah.
So convolution itself is defined as by complex multiplication of two function in which one is reversed.
No, convolution is not defined that way. Convolution, if you have f
Because
of t, and
how we define it in its integral form, the
right.
function itself which is defined, it is defined in that way. And
So,
practically we
so go ahead.
uh, we actually slides one function over
Yeah,
second, keeping it
yeah,
fixed
yeah.
from by reversing other second function and slides and
No,
find the product of
you don't
and
reverse it. Let's say that this is your function, okay?
okay.
These are the time samples. And then this is the second time series, okay? So first of all, you multiply, add, okay? So this gives you one output, okay? Then what you do is you shift this one, for example. And now, okay? And that gives you another one, okay? And the next what you do is you add this one and remove this one, okay? Now, what? So that's convolution, okay? Is that what you're saying? Or you
Yes.
dis
Yes.
okay. So in cross correlation, what you have to do is, let's say that my f of f2t has four elements, right? A1, A2, A3, and A4, right? Okay.
Yes.
So what you do here is you start with A4, A3, A2, and A1 in the reverse order. Okay. Somebody saying something?
No, that's fine.
No, I'm hearing some.
Uh, yeah,
No, sir.
Ajay, you can mute yourself.
No,
Is this clear?
Yes, sir. I think it is clear now.
Yeah,
You have reversed it and then you are
yeah,
sliding now.
yeah. So that's your cross correlation. So in frequency domain, what happens is that you have f1 omega, right, times f2 omega, right? This is multiplication. This is your this is your convolution. But cross correlation would be f1 omega f2 complex conjugate. Okay, so complex conjugate means it's e to the power minus I omega t. Okay, so it just flips the time series. Okay,
Yes, sir.
okay. So how does it work? So here I was showing you a simple experiment where I have a plane wave source here and a plane wave source here, and these are the receivers. So if you look at the recording at receiver 1 from source 1, then the source 1, it sees the direct wave and a reflected wave, right? From here. And then receiver 2 will see the direct wave and also the reflected wave. Okay. On the other hand, from source 2, you will only see the transmitted waves in both of these. So that's why, and the reason they're time delayed is now, so it depends on what time it's coming. So at R2, you get the transmitted wave arriving earlier because this is closer to this, and this one comes later because this is further away from this source. So now when you do the cross correlation, what are you going to expect? You're going to expect that one of these is a source, another is the receiver. That means you actually see a direct wave and then you see a reflected wave, right? And when you do the cross correlation, you get this, and also it goes to the negative time, and that you can ignore. So you can see that this is the direct wave and this is the reflected wave. Okay. And this is, I was showing this in a more explicit form. Okay. So if you write down all of these exponentials for the time, this is what it looks like. So this actually works quite well. Remember, this one does not require any velocities, right? So we can just, let's say that I have this virtual sources and we have the receivers here, and then we can cross correlate and do this. Now this is not exactly the same as what is done in Marchenko, because this also requires this does not require the wave field, but the ideas are very similar. I'll show you in a second. So here they use something called focusing function. And now I'm going to talk about Marchenko. So they use something called focusing function. So the Marchenko approach introduces, this is the function of the wave fields that when injected at the surface focus at a point at an arbitrary location x sub a at the initial time t naught. So the physical interpretation is that imagine injecting a wave field at the surface such that it converges to a point at t equal to 0. So it produces no downgoing energy. Okay. So here, again, I have skipped a lot of the math. In general, you can split your wave field at any depth into an upgoing and a downgoing wave field. Okay. So what you're recording on the surface is all upgoing wave field, right? Because there's nothing coming from top here. Unless you are in a VSP geometry where you have waves coming from up and also coming from down. So then your gradient, vertical gradient of the pressure would be the difference between these two. And now let's say that this R is my reflection response. This is the upgoing wave field recorded at x sub s at the surface due to an impulsive sources, downgoing source at xs prime. So first you have to define a focusing function, and let's say this focusing function f plus is my delta function. Okay. And then upgoing focusing function is related to this downgoing focusing function simply by multiplying with the reflection. Okay. And then summing over all the sources. So combining this and then using representation theorem, Wepner derived this Marchenko integral equation. Okay. Saying that I can do f plus this, and then I sum this, and that gives me both negative time and positive time of up and down going wave fields. Okay. And this fd plus is the direct wave. Okay. So what we needed to solve the wave equation, Marchenko equation, is the reflection response R at the surface that is measurable from seismic data. Initial estimate of FD, which is the direct wave. Okay, so we have the data. We need the direct wave. For direct wave, you can perhaps compute theoretically, or you can window certain part of the data itself. But to be able to do that, you have to know the time, and to know the time, you need to some smooth velocity. So the velocity requirement here is not at all strict. Okay, so you can simply trace rays and then see what is the first arrival phase. Okay, that is your direct wave, and you don't need any detailed subsurface model. And once you propagate this through using a Marchenko series, then it actually includes all the internal multiples. Okay, so this is like very similar to Born, except for the fact that it converges, and it converges in only the 3-4 iterations, maybe 5 iterations, but it can also take into account multiples in between. So let's say that I have data collected here, and I want to go to this datum. They don't have to be flat, and we have all of these internal multiples here also. You can basically take all of that out of the data and come onto here. Okay, you don't need the velocity. You need two things. You need the data, and you need the direct wave estimation. So that is the basic principle, and then this whole thing is done using multidimensional convolution and deconvolution, and this is a cross correlation thing is also can be considered deconvolution. That's another thing. So practical workflow would be you need to have reflection data acquisition, you need to do reprocessing, deconvolution for removing the effect of the source if you desire. You need smooth velocity model, you need direct arrival computation, and you need Marchenko iterations. This will give you Green's function retrieval. Then you can use it for dedataming, you can use it for imaging or whatever. Okay. Yeah,
So
and
there is a
remember, yeah.
yeah one question says, so this happens layer by layer because we are uh,
No,
having direct arrival.
you just need to have the direct arrival estimate, but you can propagate it through any number of layers. It doesn't matter.
Okay, so the direct arrival is through the first layer only, right, sir?
Yeah, it could be cutting through different layers. Yeah,
Okay, it depends. Okay,
yeah.
okay,
Okay. So for that, you need the smooth velocity model. Okay. The first arrival, rather, not direct arrival, the first arrival.
okay.
So this is the workflow, and it turns out that there is a repository where you can find the code. I don't know if you looked at that.
No, sir, I have not seen it.
I can show you in a second. Okay, can you see this screen?
Yeah, yes, sir.
So they have, so this is PyMarchenko. This Python library provides a bag of Marchenko algorithms, and it's very easy to build. I actually ran it on my machine after downloading this. It works really well.
Okay,
So you can do target oriented receiver redataming and things like that. And there are some notebooks here you can look at. Are you able to see my screen now?
yeah, yes, sir.
Yeah, so they have shown here there's an input file, so we can get all of this as a data, and this shows you the model and geometry. So these are the sources and receivers on the surface, and say this. So you want to propagate it through this and then bring it down to this, right?
Okay,
So this is the data. You can do it for multiple points, and you run this code and see these are the shot gathers at the surface. It has multiples also. Shot 50, 101. This is just samples of different shots. Then this gives you G and G naught, all those terms that go in here. And then this is how it windows the data to get the direct arrival. So that's your direct arrival. And then you run this And this is what it looks like. Okay. So these are different steps. These are the gathers. So this is the true gains function, and this is the one estimated by Marchenko, and it shows you here in the right panel. It shows you comparison between the two for a single trace. So you can see that there's a bit of a noise, but in the front of the early arrivals, but otherwise the match is quite good.
So when you say true, this is the after modeling, right, sir? True
Yeah, I
modeling.
just modeled it.
Okay. Okay.
Yeah, yeah, yeah. And so, they have done it for multiple sources also. And I didn't go into glorious details of this. I just ran their own notebook and I haven't. So this is an
Okay.
example where they had multiple locations to which they have redatamed. And that is the direct arrival. And then, and finally, they will show some comparison at the end. Okay. So this is a Marchenko series. If you did a single scattering, this is what it looks like. And then once you put multiple ones, then starts to converge. Okay.
So you had a paper on FWI where you used rewritten. Was it the same Marchenko series, or I've not read that paper, but I've heard you have done written
Oh,
string
that
paper.
was using Kirchhoff method because water layer, you don't have anything there. When
Okay.
the when the water layer multiples are removed, so it does that. So the only
Okay.
thing is that it water layer has to be, you can it's a bit tricky because what we did here there is that we redetermined it not at the seafloor but slightly above it, so that because if the seafloor is rough, you cannot you cannot downward continue all the way without knowing the velocity, right?
Yeah.
And even if so, you don't have to know the water velocity. You can downward continue unto the seafloor, but then your surface becomes rough, right?
Yeah. Yeah.
And but if you want to go to a flat datum below the seafloor, then you have to know the velocity of that particular part.
Yeah.
So it's best to actually go to a depth slightly shallower than the seafloor and then do the inversion from there on.
So do you have, sir, I mean, similar to pi Marchenko for the Kirchhoff integral redetermining?
I have to check. Yeah, there is some code available. I didn't write it. It was
Okay.
somebody else's code that I can get that, I think.
Okay. Okay, sir. Yeah.
Yeah, yeah. Yeah, in fact, a lot of the
Because
marine data people are using that for redataming.
yeah, because unnecessarily there is a lot of computation being wasted for
Yes.
the water layer.
Yeah, yeah.
And
You
sir,
can
one
actually,
more.
yeah, go ahead.
So when we are using this Marchenko, let's say when you're
Yeah.
doing an FWI, we all know
Mhm.
that in the shallow part, it gives better resolution, but as the wave propagates down, the resolution
Yeah.
is not very proper. So can we utilize this redetermining layer by layer and improve our deeper resolutions?
Well, it gives you what you have in the data, right? So I think where it might help you because your illumination is better, you go deeper and deeper. So
Yeah.
I think my hope is that it will, but I don't have any practical experience running this, so I
Okay.
will not be able to give you a concrete comment on that.
No problem.
Okay, any other question from anybody? So we take a 10-minute break and come back. Maybe they can, in the meantime, look at the quiz, but we'll not do the quiz right after that. I'll have few talks. Okay.
Okay, sir. Yeah.
Okay. I'll see you soon.
Yeah,
Okay. I'm back now.
yeah, sir.
Okay. Any question? before I start on the next topic. Okay, so the next topic is some basics of inversion. Am I sharing the screen now? All right, you can see my screen,
Yes, sir.
PowerPoint.
Yeah.
Okay, so I will give you some, we'll have some discussion on the fundamentals of inversion and then look at optimization methods. So typically we have certain set of observations, like we have gravity data, we have magnetic data, we have the seismic travel time, amplitude, and all that. And then we have subsurface parameters that we're interested in deriving, like density, susceptibility, resistivity, wave velocity, density, and so on. So our methods all indirect. We do not directly measure density. We are measuring gravity anomaly, and from there we're trying to derive this. So there is physics that relates these parameters. And here for gravity, it's Newton's law of gravitation. And for seismic theory is what we use for describing seismic data. Now, the forward modeling is what has been the topic of our discussion for the last few weeks, where we went over the details of how we can compute our data for a given distribution of subsurface parameters, particularly for seismic wave propagation modeling. And we saw that it's based on physics almost entirely. And the forward modeling can be used for data interpretation, server design, testing of some algorithms, and most importantly, inversion. And for simple bodies, we have analytic formula for forward modeling, and however, for general heterogeneous media is something that we're interested in. Numerical methods have to be made use of. So let's look at some naive definition. Of course, the basic definition is derivation of earth parameters from seismic data. So we have some set of variables, and here we have model parameters like for reservoir engineers, porosity, permeability, and so on. And for us geophysicists, VPVS and density. However, in our measurements, we have, say, for example, oil production data, flow data. For us, we have seismic data. So when we go from physical variable to measurements, it's a forward problem. We already talked a lot about forward problems. When you go from measurement to physical variable, it's the inverse method or inversion. That's how we commonly describe inversion. And you might notice that I'm calling it a naive definition. So the reason I'm calling it a naive definition will be clear from the next slide. So the way we actually do the inversion is try to use reverse physics, go backward in physics. So model based in that this does not work. It was done earlier, but it didn't work. Like layer stripping methods, because it grows with depth. So what we use is called model-based inversion or iterative forward modeling. Means we assume an Earth model, we solve our forward problem, generate synthetic data, we compare with observed data, and if there is a match, we say that we have found the subsurface model. We stop. If not, we update the model and go through this loop. This updating the model is not done manually. It's done using certain set of mathematical rule, and finding the optimal model basically is using something called optimization. So the reason I call this definition naive is that our problem is what we call ill-posed. In other words, we can expect multiple solutions satisfying the data. Say, for example, you have seismic data only within limited offset. And you know that in that case, you can get the travel time fitted by a whole bunch of velocity models. And then, so what it means is that some part of the model are not identifiable by data. So as you go deeper and deeper inside the velocity model, if with the constant offset, you know that you cannot really resolve velocities up to beyond certain depth. And we have noise in the data. So all of these things together tell me that this approach is actually naive in that sense. Yeah, we found a model, but what is the guarantee that this is the only model? An even more important question is, what is the guarantee that the model is geologically meaningful? And that's where all the work goes on when you are setting up an inversion. And then this gentleman, Jackson, the famous scientist, he said that inversion basically means interpretation of inaccurate, insufficient, and inconsistent data. So we never have accurate data, we never have sufficient data, we never have consistent data. That is real life. And then we're asked to build a subsurface model. If you go strictly by mathematics, you can always say that it's not possible to get an answer. Or you can say, you can go to your boss and you can say that I want you to basically shoot seismic data with, in the marine case, a huge amount of seismic data. Otherwise, I cannot tell you anything. If we say those things, we lose our jobs. So our job is to get the best of the most out of the data that we can. And the best way of doing this is to not just say that we have an answer, but also quantify some uncertainty. So the best way of describing this would be we know that if you go forward from model to data and go inverse from data to model, you can never expect to get the exact model, even with synthetic data. And we have demonstrated that many times. So the best we can expect is some kind of estimated model plus some degree of uncertainty. Okay. But then uncertainty quantification is also a very time-consuming task. But we will not discuss it in whole lots of detail. But I'll show you another trick called regularization. So here we have the data vector. We'll use this notation. These are the samples, data samples. In our case, this could be a sample from a seismic trace, and then all the seismic traces are concatenated as a long vector D. And this is your unknown parameters. This is your unknown. It's a model vector. This could be, you can discretize the model in terms of grid or layers. So these will be like velocities at each grid locations. And that's our forward modeling. And here we spent 4 weeks talking about this. Different ways of doing the forward modeling. One thing that you notice is that the number of data points and number of model parameters are never the same. But there's one other thing that we have to consider or keep in mind. Well, first of all, we learned about D equals GM, how to solve it. The next thing that we need to think about is when you were generating synthetic data, comparing with observed data, how do we measure the difference? So one easy way of doing is to simply taking the difference of the two and then sum. And we call it norm or objective function. And here I have this symbol that represents a norm, and I'll show you a little bit more on that. So when our forward modeling operator can be transformed into a matrix times vector multiplication, That's our linear problems, and we have analytic solution for linear problems. Okay. For quasi-linear problem, we can just expand it in the Taylor series, and then we have a linear problem. But in general, we have to solve the nonlinear problem. So the way of doing this is to first define a measure of the difference between observed and synthetic data. And then I told you about non-uniqueness. So what about if we put in a constraint that my answer is not very far from a particular known model, which is called a priori model. So this measures the difference between your current model and the prior model. And this is a weight. So if this is very high, then you are ignoring data fitting. If it's very low, then you are ignoring the prior model. So this has to be chosen judiciously. So we have two terms here. If I use simple L2 norm, I'll talk about that in a second. So this is my data misfit, and that's my model misfit. And these are the weights. You can apply weights, different weights to the data. All data may not be equally good. There may be some data that are noisy, for which you can put small weight. And for models also, you can do the same thing, because you trust some parameters more than the others. So here are some examples of inversion. So this is basically inversion of 3D gravity anomaly. We'll skip those because you're familiar with most of these things. And I'll talk about norm. Okay. So the inverse problem now reduces to determining the models that minimize the misfit between observed and synthetic data. Okay. So here I can simply take the difference between observed data and synthetic data. So synthetic data is computed using this. Okay. Now, is this the only way to compute the difference between the observed and synthetic? Is the only way to measure the differences? Now, it turns out that there is a general class. It's called a norm, and an LP norm would be like take the absolute value of the difference here, raise it to the power p, then sum over all the samples, and then take the pth root of this. So if you take p equals 2, this is simple. This simply means you take the d observed minus d synthetic square, sum, and then add. And you are familiar with this, right? This is square error. And if you divide by the number of data points, this is your RMS, root mean square. And that is called L2 norm. Now it turns out that, and you can write this in vector notation, something like this. But then p can take different values. If you say p equals 1, then you're simply taking the absolute value of the differences and summing those. And this is your p equals 2, and then it could be it could be any number. Okay. So the question is, which norm should we use? And does it make any difference as to which norm we use? So when the norm p is very high, then it's basically just the maximum value of one element. So which norm to use, and does it make a difference? So here is an example of fitting a straight line. So these circles are your observed data points. Okay. And obviously, it's noisy data. And here we've used different orders of norm, L1, L2, L infinity. And what you see is, to answer the question, does it make a difference in terms of what model you get? What's your answer looking at this?
So it does make a difference
It does
when
make a
we,
difference.
yeah.
Right. So what kind of difference is it making? What is happening here?
I mean, if there is an outlier and if you increase the norm, then it is not the best representative of the majority of the data.
So when there is an outlier, the norm is basically is attracted more towards the outlier, right? Higher order norm is more attracted toward the, it's actually L15. Okay, so that's good. So it does make a difference, but then which one should I use, right? So it turns out that you have to have some idea about the noise in the data. Okay, so when you have long tails, then your outliers are common. So use low norm. When you have short tails, outliers are uncommon, and you use high norm. So what I'm saying is that it all depends on the noise and the level. So what you see is that visually L1 looks the best because it ignores the outlier. So L1 is the best for ignoring the for discarding the outlier, right? However, in general, we don't have a very good idea about the noise in the data. And that is why most frequently, we use L2 because L2 is sort of a good compromise. Okay, and it actually seems to do a reasonably good job. So anyway, so this should tell you that it does make a difference. So now if we look at our linear inverse problems, D equals GM, this is simply a linear operator, and G is a matrix which is not a function of M. The solution is given by G inverse D, but we cannot get the inverse of G because first of all, G is not a square matrix, okay, because your number of data points and the model parameters are not the same. So the inverse does not exist generally. So we define a generalized inverse GG and we basically approximate it. And the way we do that is, we'll skip this overdetermined, underdetermined discussion, is we do a least square. So this is my L2 norm written in this vector notation, D minus GM transpose D minus GM. You can actually write this simply as some y minus x plus b and things like that. So there are in 1D you have only, in 2D you have only two parameters. So anyway, so here we have this, and then I take a derivative of this loss function with respect to m and goes to 0. This is objective function. Okay, this is called objective function or loss function in machine learning. Machine learning community calls it loss function. So if you take the derivative with respect to 0, with respect to m and set it to 0, then you get a closed form solution for the model. It gives you an analytic formula for computing the unknown model, which is given by this. Okay, GTG inverse GT times D. So now what you see is that this is better manageable because GTG is a square matrix, right? It can be inverted as long as it's not rank deficient, right? If it's rank deficient, then you have to do something else. So this is our solution for the linear problem. It's one step, it's not iterative. So for nonlinear problem, of course, you have to do something different. I'll have to skip these. So some of the linear inverse problems, we have gravity and magnetics, seismic tomography. These are some inverse problems in geophysics and medical imaging. So let's look at a very specific example of a straight line, okay? So let's say that I have a borehole and there I have thermometer that is measuring the temperature as a function of depth. And I'm assuming that the temperature is increasing linearly with depth. So I fit a straight line, but I want to know A and B, the intercept and the slope. So this is my model that I'm trying to fit. So this is T1, A plus BZ1, T2 equal to A plus BZ2, and so on. So you can write this in matrix vector notation. This is my data. This is my known model. So you have n data and two model parameters. Okay. And that makes it equals GM, and you can actually solve it using simply GTG inverse GT. Now, I may want to fit a parabola. Okay, so it's A plus B Z C Z C Z squared. So is it a linear or a nonlinear problem? Any answer?
It's a linear problem.
It's a linear problem because it's linear in the model parameter, but it's nonlinear in depth. So you can write this as D equals GM. And even though the equation is linear in data and model parameter, it's not linear in the auxiliary variable depth, Z. We're not solving for Z, so it's okay. So one nice example from geophysics is the gravity example. It's a natural source experiment, and we have the gravity anomalies. These are represented by G, and this is the coordinates of the observation point. And what we're interested in the density and the shape of the body, right? So what's our forward problem? Forward problem is very simple. In 3D, it looks like this. G is a gravitational constant. There is a density term and there is this distance term. So if you have anomaly here and then you are computing the response, this is what we need, this distance. R cube in 3D and R square in 2D. So is this a linear or a nonlinear problem? So distribution of density and also the shape, these are the two unknowns, two sets of unknowns. The first approach would be to assume that you know the shape of the body and you estimate density. So now remember, the shape of the body is basically coming in here in this equation as R cubed, right? So this is the nonlinear part. So if you keep the shape of the body fixed, this is, you know the shape of the body and only trying to solve for density, it's a linear problem. Okay. So this can then be cast as a linear problem, and then you can solve for density. On the other hand, you define the distribution of density and try to find the shape of the body. And this is your nonlinear inverse problem. So gravity is a classic example of non-uniqueness problem. Because if you have, let's say that you have a body here, a certain density delta rho, and this is the depth, and you are measuring certain anomaly. You can show that you can take this body to another depth with a different anomaly, and it will give you the same data. So what this means is that it's impossible to solve for both density and the shape of the body. Okay. So we keep one or the other fixed and then solve out in the problem. But there are some tricks of even tracing that. But generally, this is what the problem is. It's a very good example of one. Yeah.
So when you say the shape of the body, that means the depth to that body?
Yeah,
Or?
depth, it contains all the coordinates, right? It could be the shape, depth, and location, right?
Okay.
So this is an interesting practical example from geophysics in which the problem can be mapped into a linear or a nonlinear universe problem depending on the objective. So here is an example of seismic tomography on the earthquake location. So you have the earthquake and you have a bunch of seismometers. And here the data is your travel time and velocity or slowness is the unknown parameter, and this can also be unknown. And the forward problem is simple, Snell's law. And you can discretize it. So these are your travel time, measured travel times. This is your forward equation. You can discretize it. So this becomes an equation, symmetric times the vector multiplication. And so let's say that I put this in blocks, okay? So here, S1, S2, S3, S4, S5, these are the different blocks. And say I know the source. So I can trace rays, and through each one of these blocks, I have that length of the ray, and I know the slowness, so I know the travel time. So what do you need to know to be able to compute the rays? It's basically need to know the velocities, right? When the velocities change, your ray paths changes. So here we have this S is the slowness, T is the time, and this is our equation. Okay. So this is a matrix times a vector. So is this a linear problem? Anybody? Now remember that these ray path depends on the slowness. So it's not a linear problem. Unless you assume that the velocity is not changing much, or the ray path is not changing much with the change in velocity. So it's a nonlinear problem. Okay. So it does not, since M depends on the model vector R, it's not a linear problem. Now the linearization of this problem assumes that the ray paths are known a priori, which is justified under a linear approximation that ignores the dependence of the ray paths or the slowness distribution. So in linear problem also they make some approximation like ray paths are straight line and so on. So linear tomography is quite common in medical imaging in some simple geophysical problem, but not for the kind of problem that we are working on. So if you look at the X-ray imaging, here we have the source and the receiver, and then we're interested in what is known as the absorption coefficient of X-ray, right? And that equation is given by this, and its solution is this, and then they linearize it using this equation, and that then finally give you this. So X-ray tomography is a much simpler problem, both from the perspective of forward problem and the computation problem. But here I have done, I've shown you something that, where is that tomography problem? Here I have chosen certain blocks to represent velocities, right? Or slownesses. How do we choose those blocks? And does it make any difference? So to explain that, let me go back to some earlier slides which I had skipped earlier. There are different problems. One is called event determined. Let's say that I have two blocks. Let's say this is my block 1. So I have velocity v1. This is my velocity v2. And I have source 1, source 2, receiver 1, receiver 2. If this is the case, then you can very uniquely determine v1 and v2, right? and this is called event determinant problem. And when you have a lot of data points cutting through all the blocks, this is called an overdetermined problem. When you don't have sufficient data point, not only by number, but also the rays are not penetrating certain part, then it's an underdetermined problem. So here is another situation. This is also underdetermined because this ray is going through both of these blocks. Now this applies to FWI as well, okay? So here, the best you can do is to get an average of these velocities. Now mixed determinant B1, where some parts of the model are very well determined, other parts are underdetermined. So typically we deal with mixed determinant problem. So so you have underdetermined, overdetermined, even determined, and mixed determined. These are the different problems, and this is true whether it's a linear problem or nonlinear problem. So now, what this is telling me is that yes, it does matter as to what the grid size is. This everything was discussed based on a certain grid size, right? Now, if I have finite grid spacing, then this becomes an underdetermined problem. All of these, right? So in general, we don't know. So typically, what we do is we try to choose the grid size as fine as possible computationally, and then we know that it's going to have a lot of non-uniqueness, so we just apply some kind of smoothing operator. Okay, and so if you go back to here in tomography or FWI, it's very important that we think about this. So we bring in something called constraints here. Okay, so let's say that this is my data vector again. This is my model vector. This is my forward modeling, and in general, n is not equal to m. And I told you mixed determined, some linear combination of modern parameters. So here, what we can do is to add some a priori information that supplement our observations. And how do we do that? It's basically it's a preconceived idea that you have about the behavior of your model parameters. Okay, and there are many possibilities that you can think of. So one could be that our model parameters are small near a given value. You have a known average value. You have smoothly varying velocities, for example, with position. And it can solve a partial differential equation or differential equation. This could be all positive. So there are many different ways of doing this. So is it dangerous to do? Perhaps. But the good news is that, we have a lot of experience about the world in general. And so why not put that experience to work? Why ask a computer algorithm to give you an answer that is not physically meaningful? Say, for example, you're working in a particular area and you have looked at a lot of data sets, so you know what the velocities might be like. So why can't you put that as a constraint to make sure that the inverse problem solves the problem and derives the model from the data with the constraint that there are certain values that it does not violate. Okay. So one way, one approach is to add another constraint in the model, and we say that the model is L2 norm. So I have a data misfit and I have a model misfit. So data misfit is D observed minus D synthetic square L2, and model misfit would be some M minus M prior square. It means it's not very far. And this is your epsilon is the regularization weight, and it's also called damping. So if you put it in there and then you again try to minimize this misfit, we assume that epsilon square is small. And this gives you a solution that is quite interesting. All it does is in your solution, it adds this term, epsilon square I. So GTG is a matrix, and this epsilon square I essentially adds small value epsilon square to the diagonal part of GTG. The diagonal element. To each diagonal element of GTG, this basically adds an epsilon square. And that is called a damped least squares. So this is very similar to least squares, except that epsilon square is diagonal of GTG. And the reason it actually is beneficial is that GTG can be rank deficient. It's not invertible because of some eigenvalues being very, very small. And we can show that by adding this epsilon square term to the diagonal, it actually adds a small positive value to the eigenvalues. Okay, and therefore you are able to invert this matrix. This is a pretty common trick, damped least squares. Then the other way would be to put some prior information. So here we say that my model is not very far from my a priori model, and this is simply matrix matrix method, or writing in terms of matrix algebra. But ideally, what this means is m minus m prior square. Basically for each element and then summing over it. So other thing you can say that my model is smooth, and the way to do that is to apply maybe a first derivative operator. This is the finite difference operator of the first derivative of the model. So multiply this with d, and other would be that it could be a second. You can apply a second order smoothing. So this is basically Laplacian. You can apply that. So the first derivative, this is the second derivative. And then you have the new value for the model misfit, where we have this is dm transpose dm, means m transpose d transpose dm. That means m transpose wm m. And this is now become more like a weight matrix. Okay. And then similarly, we can also add some weight to the data. And so now we have weighted least squares, and this is given by this. And we have analytic solution. So for all of these, since they are all linear problems, you have analytic solution. But I'm not going to talk about them. I don't have repeated some of these things. Okay, so what we have here is, first we started with E equals D minus GM, right? Then let's call it an L2 norm. Then I said, okay, here I have a new objective function, which is my E plus phi, E plus L, which is my model norm. And one of those would be simply E plus M transpose M. Then phi 2 would be your E plus M minus M prior. and so on. Okay. So typically we have two-part objective function. One is the data misfit, and another is the model misfit. And this model misfit can carry smoothness constraint or any other thing that you want. Okay. Now this objective function or loss function is not just particular to a linear problem. The same kind of way you can define loss function for nonlinear problems also, except for the fact that this is going to be a nonlinear operator operating on it. Okay. And there is no analytic solution. Okay. Okay. Any question on this before I move on to the next topic?
So, sir, when you say analytic equations can be, I mean, rearranged into matrix form,
Yeah.
and the matrix can be inverted. So, but why don't we do in case of, let's say, Tenet or, I mean, any other analytic form of seismic wave?
No, but Kenneth's
Except,
approach is not a linear problem. It's a nonlinear forward problem.
okay, though it is
So
analytic.
yeah, you're computing analytically, but your problem is nonlinear.
Okay, okay.
Okay, so I will briefly talk about optimization. Can you see that screen?
Yes, sir.
And then after that, we can discuss. We'll have discussion. Okay, so I talked about linear problems where the solutions can be obtained by a simple analytic formula like GTG inverse GT, and also the damped least squares and weighted least squares. Now, here we'll look at some of the local optimization and little bit on global optimization. Okay. So our problem is to search for the minimum of an objective function. Okay. And this is my objective function, d minus gm, d minus gm. This is the basic one, but then we can add some model norm to it, and you can have another lambda term here if you like. Or in case of statistical method, we use covariance, data covariance, and model covariance matrix. In deterministic case, we were calling those weighting. And this is a very general way of representing this. You can have a smoothness constraint. You can have a priority model and all of that stuff. And there is no reason for us to have L2 norm for both. You can have L2 norm for data, L1 norm for model, and so on. Of course, there are some computational difficulties, which we'll talk about briefly. So how do we actually find the minimum of an objective function? And for a nonlinear problem, we have a loss function that looks more or less like this. So what it means is that if we change the model value, it may go down, but then it may start to go up again in error. And so you can see that there are some minimum here. And all of these minima are called local minima. And when these local minima are very close together in the sense that if you move a little bit from there, the error does not change much. These are called weak local minimum. And when you move a little bit away from the minimum point and the error basically increases, those are strong local minima. And the minimum of all minima is called global minimum. Ideally, we would like to find the global minimum, but there are some practical difficulties. So we try to basically work with local minimum or rather local optimization most of the time. So here, so what happens is that local minimum problem is something that has plagued us for a long time. And the main problem is that when you are using a local optimization method, it's very sensitive to the choice of the starting model. If you started here, then you can find the global minimum. If you started here, you're going to find the local minimum. If you started from there, you found the local minimum. So, and then there is other method for global optimization, and that can be, that is not that sensitive to the choice of the starting model, but then it's computationally very expensive. So if I want to use local optimization method, before I talk about how they work, there are ways people try to mitigate this local starting model problem. One is work very hard to get a good starting model. That is to play with the loss function in such a way that it becomes more like a smooth loss function. So there is a broad minimum, and once you are close to it, then you can start to refine your objective function values. Prior to that, you use local optimization. So local optimization plays a very, very important role. So here we have a starting solution, and this is a model algorithm, and then we compute our synthetic data. If they match, we say stop, or when there's a convergence. Otherwise, you compute a search direction. Let's say that in two-dimensional space, you're trying to find minimum value, right? And you've started from here. So you have to know which direction you want to go to. There are multiple possible directions, right? And once you find a direction, you want to know how far you want to go. So these are the two important things. One is the search direction, another is step length. Once you have found those, then you can update your new model, find a new search direction, and then go. So there are many methods. In geophysics, you can see mostly people using Newton's method, steepest descent, conjugate gradient, and so on. Now, steepest descent, what it does is simply computes the gradient of the loss function, objective function, okay? And so it goes in the negative direction of the loss function. And that is because the negative direction of the gradient. And then it also has step length that tells you how far it wants to go. And then it repeats for a certain number of iterations. So here is a sort of cartoon in 1D. Let's say that this is your objective function and you want to try to find the minimum. You started from here and you computed the gradient. Now you want to go in the negative direction of the gradient. Okay. So you go in this direction. And then you have a step length that tells you that you want to go here. After that, once you are at that point, you again compute the new gradient. Go in the opposite direction, given the step length, get the next point. And if you repeat it a few times, so this is the basic algorithm that is very common in many of the optimization problems. Just compute the gradient. So you have to be able to compute your forward solution, f of m, plus you have to be able to compute the derivative. So these are the two things that you have to do. Now, so this is your gradient descent. So there are things that you have to worry about is like what is your starting point and what is your stopping criteria and what is your step length, right? And these are the things that we normally decide based on our experience with working on a particular data set. Because in noisy data, the error is never going to be zero, right? You want to get to a certain small value. And it's not even a good idea to go to a very, very low loss function value, because then at that point, you might be matching the noise. So this is how a local optimization method works, or the gradient descent method works in terms of finding it. It turns out that if we have like a narrow valley type of objective functions in 2D, then it takes a lot of steps to get to the minimum. It's called the ping pong effect. And that slows it down. It works, but it slows it down. So for that, we use something called conjugate gradient. Rather than going into the actual space descent direction, we go into the conjugate direction. Again, I will not go into details of the theory. The algorithm is written here. One other thing that we need to look into is called Newton's method. This is called second order method because it requires not just the first derivative, but also the second derivative. And the way it works is that you have your objective function, you expand in a Taylor series. This is the gradient term, and this is the second derivative or curvature term. And it turns out that your model update is going to be the current model inverse of the second derivative matrix times the gradient. So it also requires computing the second derivative. It turns out that if you have the Hessian, then it actually gives a much better solution and it converges quicker. And the reason is that rather than fitting going in the direction of the gradient, it actually at every point it fits a parabola, and based on that it decides what should be the next step. Okay, so here so local optimization method, as I told you earlier, it finds the best fitting model. You need to compute a search direction, you need to compute a step length. So if it's a gradient descent, you need the gradient of the loss function. If it's a del E del M, if it's a Newton's method, you need del 2 E del M2. Now this one, already a forward problem is expensive to compute. Gradient computation is also expensive. Now you're talking about second derivative. Now second derivative is even more expensive. So typically we use some approximate method where we try to use the gradient information to approximate the Hessian. So we never really use full Hessian, we use an approximate Hessian. Okay, and those are called quasi-Newton method. Okay, so what about not doing local optimization? If we just do global optimization, one approach would be to search the entire model space. Okay, so for example, if I have a data point that looks like this, and this M1 and M2, these are the parameters, and add some noise to it, this is what my data looks like. But I can compute the error in a multi-dimensional grid and choose the grid point with the smallest error. Now in this case, we can afford to do that because this is only like a 2-parameter case. So this shows you the error function for different values of M1 and M2, and your minimum is somewhere in here. Okay, so look, you can see how much, what is the landscape of the loss function. It's typical in many hills and valleys. Now, to be effective, the number of parameters have to be small, and the forward problem has to be computed fast. So this grid search is not practical. There's something called Monte Carlo method. What it means is that compute the error at some randomly generated points and choose the points with the smallest error. So this one shows you pick some different random model parameters, and you can, if you're lucky, you can find the best solution. The advantages is that it does not require a specific decision about what the grid spacing should be, but this process is open-ended. It can be continued as long as desired. The disadvantage is that it might require more time. Now, simulated annealing is a Monte Carlo method, which is completely undirected. So it's a Monte Carlo is completely undirected. Newton's method is completely directed. Monte Carlo is slow but foolproof. This is fast but can fall into local minimum. So what about we want to add some partially directed random walk? So let's say that this is my starting model. And so then we can actually use something called simulated annealing. And the way simulated annealing works is, think of this analogy with annealing of metals. So let's say that you have a substance that you heat it up to a very high temperature. So it's in a sort of high energy state and with the atoms are randomly moving across at thermal motions. But then if you start to cool it slowly, they can form crystals as shown here. However, if you cool it too fast, then it will form glass, which is basically local minimum of the energy function. So using the same analogy, what we can do is something called a temperature T. So let's look at one example. So this is my energy function that has been turned into a probability distribution. So what I do is I take the loss function and I do the exponential and divide it by some parameter T. So this is a control parameter. It's called temperature. It's not a physical temperature. It's just that from the analogy with from physics that I showed you earlier. So how does the shape of this function change for different values of T? You see, if the T is very high, then this looks like every solution is probable. Now, as you slowly reduce the temperature, you can see that the global minimum becomes the most probable. So this is the idea of simulated annealing. Unfortunately, this particular example, I knew the loss function value everywhere, but in practice, we don't. And it turns out you don't have to know it at every point. So the way it works is that you start at some location, and then you pick a new location, M star, from some proposal distribution, and then you decide you want to keep it or throw it away. And you decide based on certain probability. Okay. So that probability has some parameter called temperature T. If T is very high, you always keep the better. You can go anywhere. Otherwise, the better models are preferred. So initially, most any model is acceptable, so it can take random walk. But slowly, when it goes to lower temperature, it actually slowly converges and finds the optimal solution. So start off with large T, slowly decrease T, and this way this is directed, similar to Newton's method, but in the beginning, it's undirected, so it's more like Monte Carlo method. It's pure random, but as you go to lower temperature, it becomes more directed. And there are some variants of it here. You can use gradient if you like, and so on. So we have a full waveform inversion code where we are actually a hybridized local and global optimization methods. Okay. So then there are different ways of doing simulated annealing. Very fast simulated annealing is the fastest one. So very briefly, I'll show you a couple of slides on genetic algorithms. And this is also one of the global optimization methods. And there's random walks in model space. So it works with a population of model rather than a single model. So here, in simulated annealing, have an initial model and finally get an optimal model. In genetic algorithm, we have a population of model, and then we update what is known as fitness as a function of generation. In the last generation, we have the optimal set of models. So here you have the data vectors, the model vectors, the synthetic data, this error function, and this could be a fitness function. So what we do here is first you have to code the model. So in this case, typically we use binary, sometimes we use real number coding also. And in analogy with genetics, so this corresponds to each bit corresponds to a gene, and I'll show you how this works. Let's say that I have a velocity going between 1500 and 1810 meters per second, and I want a resolution of 10 meters per second. So that means I need 5 bits. Okay. So when all bits are off, this is my minimum velocity, which is 1500. When the lowest order bit is on, it's 1510. This is your 1520, and when all bits are on, this is 1810. So what we do is we choose a range of values, say for a particular layer, okay, range of values for velocity, and also a resolution, and that tells us how many bits I need. So if I have say 10 layers, if I need 5 bits for each layer, then I have 50 bits, okay, and that forms a model. And then what we do is this is another way of coding. Go through these 3 steps: selection, crossover, and mutation. And these are done using certain probabilities: selection probability, crossover probability, and mutation probability. So in selection, we choose a population from, so let's say that I have 100 models in the population. So I make 50 pairs. Before I do that, out of these 100 models, we select 100, some of them would be repeated, and this is a bias selection. Any model that has higher fitness value has a higher probability of getting selected. That means better models are selected with preferential selection scheme, and the worst models, that means the ones with low fitness values, are rejected. So this is the probability of selection. So we started with hundreds, we have new 100 model, and some of those are repeated, right? So if we just did that, then we'll end up with the same good model that we started with at the very first place. So there are other things that we do. It's called model mixing. This is your crossover. So we choose pairs of models, so 1, 2, 3, 4, up to say 100, and then we choose a crossover site, for example here. And then what we do is we just swap the value. So where there was 1, go to 0. This 1 and 0, these are swaps, so it becomes 0, 1. 0, 1 becomes 1, 0. 1, 1 becomes 1, 1, and so on. And we choose that only to the right of the crossover point. And this crossover is also done with certain probability. So that could be a single point crossover or multi-point crossover. We found that the multi-point, actually I wrote this was the first paper in 1991 ever done in geophysics. So this was very early work that I did. Anyway, so, and then both similarity annealing genetic algorithm I wrote in 1991. And in fact, I actually don't use genetic algorithm. I gave up because it's very slow compared to simulated annealing. And then we do, so this is a single point crossover, and what I showed you. Then the last thing we do on this is mutation. So in mutation, what we do is randomly flip one bit. Okay, we pick a bit at random and then randomly flip it. So that introduces diversity. Okay. So here shows you how we take this and then add a new location here. So in this process, now there are other ways of doing this. And here also we introduce the concept of simulated annealing, but I'll ignore that. So the recipe is that we start with a population of models and then repeat over a bunch of generations, evaluate fitness. That gives you maximum fitness, average fitness. Then you update models in current generation. This is the selection process. using this particular selection probability. Then you apply genetic operators, crossover and mutation. And here I used a little bit of concept of simulated annealing in the 1999 paper, 91 paper. You may or may not want to do this, but this makes it much faster. And then you loop over generations. Okay. And after a large number of iterations, it does. So the problem with SA, I mean, the pros and cons is convergence to an equilibrium distribution. So this is statistically more rigorous in terms of actually sampling from a distribution, of course, without changing the temperature. The convergence may be slow in some cases. And of course, now our newer method with gradient descent, it actually converges pretty quickly. And VFSA is quite fast. GA, the convergence is not proven to the global optimal, but in most cases it does work, but it can be very, very slow, and the number of and the members in the population have to be pretty large. So this was a very early example of what we did. So this was a tau p seismogram, and these are the different layers. And this is what I still like. And what I have here shows you for different layers how the velocities are changing as function of different generations. You can see that these are all different models, and then it slowly converges to the best one. And when I looked at it, I realized that there's something called diffusion model in machine learning, and I was able to relate it to that because this was a noisy data going to the denoise state, and that's quite exciting. So this was really a very sort of enjoyable journey, being able to explore all of these different methods and then choose the ones that kind of start to make sense and practical for some of the applications that we're interested in. So this is where I'd like to stop, and then we can have some discussion rest of the hour or whatever. And maybe you can talk about the quiz. Any question, comment?
So there is one question from my side. Like we
Yes.
have different kind of modeling like Canet or a convergent bond series or complete wave equation using finite difference. But
Yeah.
all these three require different optimization. I mean, some require
No,
global
no, no,
optimization.
no,
So,
no, no, no. Optimization could be anything.
okay.
You can use either optimization method or any of these things.
Yeah, but it can be used. But normally, when if you want to reach to a global solution, let's say we are using a Canet-based conversion. So, in most of the cases in your paper as well, you require a global optimization.
No, that I wrote many years ago, but nowadays I use a robust local optimization method. I don't use global optimization. And it
Okay.
converges in 10-15 iterations.
Okay. So it will be very fast.
Yeah, yeah, yeah.
Okay. Okay. So this was the confusion because in earlier Subhasis Malik's paper, what I saw that he uses genetic algorithm
Yeah.
and okay. Okay, no problems.
I mean, I showed FWI also using global optimization.
Okay.
Then it has, yeah.
So how does that compare, sir? If you use, let's say, a global versus a local optimization in FWI, does the result
Well, it's
make
very slow. You have to have, we can only do that for a few parameters.
okay? But how does the result compare?
Depends on if you don't have a good starting solution, obviously global method works better. Maybe you can turn on your videos so I can see who I talked to for the last few weeks. People are shy.
So, Arun, can you put your camera on? All of you, I mean, yeah.
Yes, sir.
So
Yeah.
Okay,
he's
hi.
Arun. He's working in UCG team, and there's some exciting work he's going to do.
Yeah, maybe you guys can introduce yourselves one by one.
Yeah, Arun, can you introduce yourself? Yeah.
Yeah, my name is Arun Kumar Veda, and I am a geophysicist with 18 years of experience in seismic data acquisition and processing. I started my career in the lens industry in 2008 and worked for near about 10 and a half years, and then moved to one company in Nigeria that is Sterling, you may be knowing. So here I was supervising the seismic data acquisition and processing projects. And after that, I came back Mumbai and worked in Aspen Tech as a processing GeoPC as a service provider. And then I moved Absolute Imaging Noida, that is also a service provider in seismic processing. In this December 2025, I joined Reliance again and looking after this land acquisition, processing, and interpretation projects.
So you are with Reliance now?
Yeah, right now I am.
I think we have two interns like Shweta and Karthik. They are I think they are in final year student.
Okay.
And Anshul is also, Anshul, you are in final year? Yeah, Anshul Chaudhary is in final year. And I think Amli is, he has recently joined. You have 3 or 4 years experience, Amli? I forgot. I think she has 3 or 4 years of experience, Amli. And I think the JP was there, he left now before introducing himself. Yes. Santosh is not here, so he is also quite experienced, around
Yeah, I met
23
Santosh, I
years
think.
experience. Yeah, Santosh. And JP was there, he is also quite experienced. Then Ajay was there, who was asking about convolution. He is also
Yeah.
quite experienced, more than 20 years experience in processing. So most of
Yeah.
them are from acquisition and processing, and rest of them are interns and newly joined people. So right now I am working with these interns to write a code for convergent bond series based inversion. So Sweta is working on that. Karthik is working on that. I just wanted to experiment with the
Okay.
students whether they
Good
can
evening,
do
sir.
or not.
Good
Yeah,
evening.
she's
Yes.
Sweta. Yeah.
Myself,
So
Shweta.
this,
I'm studying in IIT ISM Dhanbad in MSc Tech Applied Geophysics, and recently I have completed my internship in Reliance CBM Shahdol. Thank you, sir.
I've given her some coding tasks about Marchinko, and
Okay.
I'm meeting them every Sunday. Just, I mean, to help them out. And he's Karthik.
Okay.
Karthik, can you introduce yourself? Yeah.
Yes, sir. Good evening, sir. Myself, Karthik Dudikatla, and I'm from MSc Tech and Applied Geophysics at IIT and then but recently completed my internship at Reliance. And yes, sir.
And so they are very good at coding. What I have observed, they wrote very quickly a code on NMO correction, whatever exercise we are given, and then plotting the gathers, picking the amplitudes. So I thought of working with them for some advanced modeling and all this. So I just picked them, Shweta, Karthik, and there is one more guy, I forgot his name. So we are
Ayush.
meeting in Ayush, yeah. So we are meeting every Sunday to discuss what we have taught and probably to, I will provide them some real gathers as well to work on that, on those
Okay.
gathers.
So if there's no more discussion, I think should be it for today. And then we have a set of questions that I passed on to Ashok. Maybe you guys try to answer those.
Yeah, we have, I think I have not able to send to the students. I have sent to the Reliance network. I didn't have their email IDs. I will send them later answer. I have to pick their email IDs. It is very difficult to remember. It is numeric numbers and all those. It is not name. Probably their
Okay.
ISM email ID. So we'll do it, sir. And then I looked at the questions. Most of them
Yeah.
I mean, correctly pick. Few of them were left. Probably
Yeah, it's
we'll
very
discuss it
simple.
later
Yeah.
on.
Yeah.
Yeah,
Very simple based on the lectures that I gave. Right.
yeah. And sir, what about the slides which I shared with you? Would you like to comment on that about the FWI? How was that FWI which I shared with you? The slides.
Yeah, I think it makes sense actually. It looks pretty good. I saw your data fit was good and loss was going down, so this is quite good. The only thing is that, yeah, so I saw, yeah, you might want to share your, you
Yeah,
have the slides here?
yeah, I will share it. I have to open my email. And sir, about the anisotropy, I mean, it's an acoustic equation, whatever I'm using in the video right now.
Yeah.
And the offset is up to 10 kilometers, and I'm
Mhm.
not restricting my offsets. So, I mean, what would be the strategy? I mean, using the acoustic, but still I want to avoid the anisotropic effect and get the true vertical velocity. So, what should be the strategy?
Well, I think you
Apart,
should ignore anisotropy to start with and see what you get. And
yeah,
then the other option would be that if you can do some kind of anisotropic velocity analysis,
okay,
and then get some estimate on epsilon
okay,
from the, and then you can just use that as a parameter.
okay. And what about, sir? I'm right now, I have worked on is I'm restricting my offset as I'm increasing my band. I mean, let's say I'm going from 12 to, let's say, 15 or 18 or 20. Then progressively I'm limiting my offset. Will that help, I mean, to get my
Yeah, yeah,
true vertical velocity? That idea?
yeah, you can do that.
Yeah, so I'm working on that right now.
Mhm.
So I ran it on Friday. Let's see. I mean, on Monday I will have some result because on the first two bands, since the wavelength is quite large, so whether it is isotropic or anisotropic, the time difference should not be much. This is the idea for the lower bands. But we are moving to higher bands.
Yeah,
Then, since the wavelengths are very small, then an
yeah,
isotropic effect can be quite, I mean, drastic. So I
yeah,
wanted
yeah,
to restrict my offset when I'm increasing the frequency. So this is the
yeah,
idea. Let's see how it goes. And sir,
yeah.
one more question. I'm not able to find the, let me, let me, the, the slides which I sent you. So the other question which I thought of, sir, can we work on elastic as well with the same derivative code?
Yeah,
Elastic
yeah,
code would be, I mean,
yeah,
okay,
yeah, yeah. That would
okay,
be very useful.
okay. And the other idea is, let's say I'm doing some small iterations on FWI. Small means, let's say band one, first band only, and using that for Kennett or convergent bond series based inversion. So, I mean, how does that work out?
Yeah,
I mean, I'm
that
just
would
wondering.
also be, that'll be worth trying. Yeah.
Okay, okay. I'm trying to find my inversion which I shared.
I
Is
may have
this,
it here.
let me click it.
I have it. If you want, I can share it.
Okay, yeah, yeah. Can you share it, sir? I have to connect to my office network.
Yeah. Yeah, you can see it now.
Yeah, yes.
So that's your first slide.
Yeah, this is band one,
Yeah.
and this was probably up to, I think it is up to 12.5 hertz, 2.5 to 12.5 hertz.
Yeah, that's your misfit. That looks quite good.
Yeah, yeah, yeah. I'm a little bit concerned about this, sir, because you see the real data, especially in the water bottom, it is very high amplitude. But what I have modeled is, I mean, the amplitude is very small. And since it is only a phase-based misfit,
Yeah,
so it is not much of a concern. But if I want to use L2 norm, then I have to
yeah.
fix this.
No, you have to normalize your data because it does not know the actual absolute amplitude in the data is not known. You
Yeah,
see, synthetics will compute the data in pressure, so there has to be at least a constant in a scale factor.
okay. Okay.
Yeah,
And this is the next band. Probably
yeah,
this is up to 15 hertz, something 7.5 to 15 hertz. And now I can see the hydrates. You can see the one just below that blue part, there is a orange or red coming up. That is the
Yeah.
hydrate which I have verified.
Yeah, and so this on the left you have this the
The
vertical stripes.
difference, yeah,
And
this is because
yeah,
of the foldage. I mean,
yeah,
I'm
yeah,
not
coverage.
going, yeah,
Yeah,
coverage
coverage.
issue. Yeah.
Yeah.
And this is still the next band up to, I think this is up to 20 hertz, and last band is up to 24 hertz. This is what I pushed up to, because otherwise it required a lot of reducing the grid size and all that.
Yeah, this one is showing pretty good fit to the data actually, not bad.
Yeah, yeah.
Phase wise, yeah. So is there anything new that you have kind of discovered in this that was not known?
I mean, the hydrate was very surprising, sir. It was not very obvious on the seismic. I mean, none of them told me earlier that this is a hydrate.
Mm-hmm.
But when I showed them this result, then I mean, I could make it out that it is starting with a peak, and it could be a hydrate because it lies in the hydrate stability zone.
Yeah, yeah,
And there
yeah.
were other reflectors much brighter than that, but that was not a hydrate. So
Mm-hmm.
this was I mean, a surprise. And because we had a workshop with the expert in hydrate from US.
Yeah,
I forgot the professor's name, and he told
yeah.
us that in hydrate we will have different kind of contrast. Even if there is a hydrate, it may
Mm-hmm.
happen that on seismic it will be blank. So this is a possibility.
Yeah,
And I'm concerned about this at this frequency, sir, because we are just limiting ourselves to the high frequency. Why not to use the low to the highest frequency? Let's say 2.5 to 24 hertz, and then check how it matches.
yeah, you can do that also.
Yeah, because we are just limiting to the high frequency, and it is becomes
No,
very
but your
difficult
starting
to match.
model,
Yeah,
but your starting model should be from the previous frequency band.
yeah, it is from the previous band, but I've showed the starting model here in the picture.
Okay, okay.
Yeah, but
So
in each of the cases,
yeah, then it's fine. Yeah.
yeah,
Yeah, this is good.
yeah.
And
So next time, yeah,
yeah, considering that you didn't really, you hadn't done this before, it's really
yeah,
amazing.
this was my first attempt. I mean, after
Yeah,
you told that DeVito can work, then I started
yeah,
experimenting with DeVito,
yeah,
and then started working on it. So I will
yeah,
next time trying with the anisotropy, restricting my offsets so that I
yeah,
get the right vertical velocity, and then
yeah,
probably I
yeah,
will slowly move to the elastic. Because
yeah,
the my aim is to do some QI work with the inverted result, not imaging.
yeah,
Santosh might
yeah,
be using this for imaging, but my target is to use this FWI plus based on finite difference and your analytic like CBS or Kenneth to get my rock properties for reservoir characterization. This is my
yeah.
idea of that now.
Okay. Good. Anything else?
No, sir. Thank you.
Okay. So keep in touch and
Yeah. So we can write some papers also, sir, based on this data because it's a very good data, 10-kilometer offsite.
yeah,
So
yeah,
if you have any idea, you can work on that. Let me
yeah,
know.
yeah,
So
yeah,
we can work on that and publish some papers.
yeah, yeah. Also, in a way, the KK Kerala Konkan Basin, if you have time to
Uh,
work on that, that'll be great.
so what is so special about that? Is it because of the basalt there or?
Yeah, yeah, yeah. So,
Okay, for the basalt. Yeah, it's, I mean, because of the imaging, there is no exploration in that block.
yeah, yeah,
So if the guy can help, then that would be a good start. So let me fetch
yeah,
that data first. I will
yeah,
locate
yeah,
that data and then I will start working on that.
yeah, yeah.
Okay, sir. Thank you very
Okay.
much. Yeah.
You,
So this would be I think the last lecture. So
yeah,
probably we will meet sometime again,
Yeah.
probably in the SEG or somewhere.
Yeah, sure. Okay.
Okay, sir. Thank you very much.
Okay. Bye bye.
Bye bye.
Thank
you,
you,
sir.
sir.
Thank you.